This video will present a basic demonstration of the Dynamix 1444 series condition monitoring system using the Studio 5000 Logix Designer software. First, I have to start Studio 5000. I'll create a new project. I'm using an L79 L8 DERM controller. That's what the demo kit has in it. And I will simply call this demo. Demo kit controller hasn't any modules in it, so we just start. Okay, that took a minute. How long it takes will depend on your particular system. And the first thing I need to do is add our module. So I go down to the Ethernet tree where I can add an Ethernet IP module. You notice there are 514 modules, so what I'll do is simply search on 1444 and I see the module here. It's a specialty Allen Bradley module, so I'll accept that. So here's our module. The first thing I'm going to do is give it a name. I'll simply call it demo, the same as before. And then for its address, for my system, it's at local address 89. The Dynamix modules can produce a lot of data. Most applications only want some small amount of that data. So we use module definition to define exactly what we want to bring back on I/O for this application. So on this first page, I'm not going to change anything. Everything there is fine. On the second page, I'm going to tell it to bring back the two speeds. And the module is capable of measuring two different speeds, perhaps from different sources. And then I'll add just an overall value and two FFT bands for each channel. Notice that there are a lot of more selections that I could choose. Which ones you choose is just a matter of the application. And now I'll copy the overall and the bands to the other channels. And that's all I want to do for input. For output, I want to send two speed values from the controller to the module. This, of course, assumes the controller knows or can get the speeds. This is also where we tell it what expansion modules that are connected. In this example, I'll add a tachometer signal conditioner, which I have in the demo kit. If I have other expansion modules, perhaps a relay or an analog output module, then this is where I would add those as well. And that's all that I want to do on module definition, so I'll apply that and we're done with module definition. Normally you need only do that just once when you first set up the module. Okay, let's raise this up a little so I can see what's going on. So now I'm ready to configure the module. The first thing I'll do is configure the tachometer. The tachometer page is shown only when a tachometer signal conditioner is attached to the module. So this page is where you actually configure the tach module. The tachometer signal conditioner can accept input from various types of sensors. Most common are either eddy current probes or magnetic pickups. And this is where I set auto trigger, the number of pulses per rev, and other parameters associated with the tachometer itself. On the speed page, I tell it where each of the two speeds come from. This is actually going into the module. The first one I'll leave as tach bus 0, which means that it will measure speed from a TTL signal from the tach module. For the second speed, I'll tell it to read the RPM from the controller output. And that's all I want to do here. I have two speeds, one measuring a TTL from the tacho and a second reading speed from the controller. The hardware page, this is where I define the physical attributes of the system, what's going into the system. For the channels, I'm going to leave the first two as they are, eddy current probes. I'll change the second one to Y so that they're XY, which is the normal way we do eddy current probes. And for the second two, I'll make those accelerometers that are going to integrate to velocity. So I have two of those. You can see that it is setting the default for sensitivity and engineering units that are common for the types of sensors, the power, the bias, the limits that tell us that the sensor is faulted if the bias falls out of range. After that, all I really want to do is set the bands. I'm going to set 2 bands per channel. And the second band I want to set in orders. The first band I'll leave as it is. It's fine the way it is. The second one I'm going to set as orders, and I'm going to set it to use speed 1. That's the speed coming back from the controller. And I'll pretend that I want to monitor vane pass frequency, which is 5 times the running speed of the machine. So I'm going to define the band from 4.9 to 5.1 times speed 1. And that's all I want to do, so I'll copy these bands to the other channels. From the bands page, the other measurement pages are all fine, and that's all I want to do. Beyond that, if I want to, I could set alarms, I could define relays, I could define other measurements, various signal processing that I might want to do, but that's all I want to do for the demo. So I'll say OK, and I'm done with that. So I'm ready to go. So the next thing that I want to do is simply download the configuration to the module. I go here to where it says offline and I simply say download. And if you don't already have the controller defined, you might have to tell it where the controller is. So I'm just going to download the configuration to the module. While it's downloading, I want to watch the status. The status will go from offline to configuring, and then eventually to running. As the module receives the configuration, it validates the various parameters to make sure it's good. And once it has it, it is changed from what it, if it is changed from what it had before, it writes it to the module's non-volatile memory. All this takes about 30 seconds. Okay, so now that that's running, I'm able to look at the tags to see what is going on. So I'll look at our tags, and on input, I'll expect to see them updating, and sure enough, numbers are updating from the module just fine. And we can see the overalls, and band 0, which is based on frequency to 100 hertz, they're all updating. But band 1, that's not updating. Band 1 was defined as being an orders-based measurement 5 times speed 1. And we know that speed 1 was being sent from the controller, and speed 1 is 0, so 5 times 0 is 0. So band 1 is measuring exactly what I would expect it to measure, which is 0. So what we need to do is to output the machine speed to the device, which we're not. So we'll tell the output 1800 RPM. So we do that, and sure enough, we see the output go to the module, which gets it. It's sending it back right back to us, and now we're measuring band 1. Now we can see all the band 1 values are updating. And that's all we have to do for the demo. So once we have tags and logics, it's very easy to implement solutions. It's no different than implementing solutions using any other I/O. Of course, there are faceplates and toolkits available to help implement a solution. Almost always customized for what you want to do, of course. Sometimes, though, the solution may be to add the tags to VantagePort or an historian so that the data can be correlated to other processes. It doesn't matter what you do with the data, how you present it, where you present it, it's simply tags. We have now demonstrated how Dynamix can be easily applied to serve any solution simply by being part of the integrated architecture.